And this next passionate speaker is Dr. Eteri Svanidze. Welcome her. Eteri is a group leader at the Max-Planck-Institut for Chemical Physics of Solids, where she studies the combination of various elements of the periodic table to design new materials with intruding chemical and physical properties. Eteri's talk today will be about these new materials, which can enhance our life and push technological advances.
Okay, thank you so much for the introduction, and thank you all for tuning in to listen to me talk about materials. So first thing I'd like to point out that today's event would not have been possible if it wasn't for the progress in the technology that we have made because of new materials. And these things are all around us. You might not even notice them. Everything from the computer or smartphone you're using to watch this talk to the credit card you use to make purchases. The weather satellite that told you whether or not you should bring umbrella tonight, or the lights at a street crossing that keep you safe. Materials make our life better. So the first question you might have, what are these magic materials? Broadly speaking, everything or most things around us are materials. And materials themselves are composed of atoms. You might ask, what is an atom? Well, atom is the smallest part of ordinary matter. So all things are composed of atoms, even humans. Atoms are very, very tiny. How tiny? Well, in an average human, we have 7 octillion atoms. Looks like a lot, right? This is 7 with 27 zeros. Let me give you another example. If you take 1 liter of water to represent each atom, the volume of this water would be larger than the volume of Earth. So atoms are very, very, very tiny, but they're also very different. And this mostly depends on the composition of an atom, because atoms themselves also have even smaller particles inside them. So depending on the type and quantity of these tiny particles, atoms look and behave differently. They're also more simple or more complex. And according to this complexity, we can arrange all atoms into something you might have seen before. This is the periodic table of the elements, in which we have atoms arranged from the simplest at the top, this is hydrogen, to the most complex at the bottom. Now, all of these atoms are very interesting by themselves, but what I'm interested in doing is mixing them together to create new materials. But one has to be careful, because you can't use all of the elements, simply because some of the elements are very toxic, some are very radioactive, some simply don't exist under normal lab conditions, and some just don't want to play with others. So what we're left with is about 80 elements. This still gives you a lot of room to play with. So many materials to discover. Now, what I'm interested in doing is mixing these elements together to create new materials. And each element has something different to offer. Just think about elements that you see in everyday life. For example, iron is very mechanically stable, so we use it to build bridges or be it part of buildings. On the other hand, mercury is liquid down to very low temperatures, so up until very recently we used it in thermometers. On the other hand, neon is a gas, and it glows, so you will see it in street signs. And elements like silver, platinum, or gold, they don't corrode, so we can use them in jewelry. Now, every element is special, but today I will tell you only about one of them. This is silicon, and I have brought a piece of silicon with me to show you because I think it looks quite cool. It's very shiny, and it has sort of metallic luster. Now, I've already told you that in this piece of silicon, we have many, many atoms. But the thing is, we don't have to worry about all the atoms. We know that in this piece of silicon, atoms are arranged in a particular pattern, and this pattern gets repeated over and over and over again. The smallest unit of this pattern is this. As you can see here, atoms of silicon are arranged quite lovely in a very organized manner. We can change this pattern if we add one more element to the mix. Let's add oxygen. You're all familiar with oxygen. So if we take 2 oxygen atoms for each silicon atom, we have something like this. You can already see that the structure of these 2 materials is very different. So are the looks. In fact, the silicon oxygen material is quartz. It looks completely different from the silicon. And the applications of these 2 materials are also very different. So what I have showed you is that we can mix elements together to create new chemical structures, and as a result, it gives us new physical properties. But the structures that I have showed you are quite simple. What I'm interested in are structures that are a bit more complex, and let me show you why. So here we have a combination of 3 elements. This is uranium, ruthenium, and silicon. Now, you can probably already agree that the structure looks way more interesting, and we're interested in this from the chemical perspective. Additionally, this material is a superconductor below a certain temperature. You might be asking yourself, what is a superconductor? Well, a conductor is anything that can transmit electricity. So, for example, a piece of wire. But the problem is, when a conductor is transmitting electricity, it heats up. This is why your laptop charger or your cell phone charger is warm when you use it. While it might not seem like a big deal, we actually lose more than half of all energy due to this unwanted heating. A superconductor can transmit energy without any losses. And this is really great because, well, we don't lose any energy. The problem is, currently, most of the materials are able to do this only at very, very low temperature. So the quest for room temperature superconductivity is one of the biggest questions in the work on new materials. And while this material is not a room temperature superconductor, it can tell us quite a bit about superconductivity. By studying this and other materials of this kind, we, or I, hope to design new materials that will help us solve problems of the future. The goal is to try and design new materials that will make our life better, safer, and more convenient. And this really applies to all areas of your life. And my goal is, basically, by doing so, not to only contribute to fundamental research in chemistry and physics, but to also bridge the gap between science and society. Thank you.
Thank you so much for your talk, Eteri. I found it super interesting, just as you mentioned, how you can combine like this inorganic chemistry with material science and physics to create those new materials. So let's get started with our question session. Just post your questions for Eteri in the chat and I will forward them to her. Maybe let me start with one first because I'm actually quite curious. So I was wondering if there is a limit on how many different materials you can actually produce.
Yeah, this is an excellent question, right? So in the periodic table that I have showed you, we have, let's say, 80 elements that we're working with. And in principle, there is really no limit because our compounds or our materials can have 2, 3, 4, 5 elements, right? So think about combinations of all the elements and remember that all elements can also have different ratios. So much like in cooking, you can combine different amounts of each ingredient to give you something new. So I would say that opportunities are, in fact, quite limitless.
Okay, wow. Then it actually comes to a similar question. How many different elements can actually be combined?
Yeah, so it is quite similar, right? So in principle, the majority of materials that we work with have 2 or 3 elements. And this is sort of a standard, but of course we can combine 4, 5, or 6 elements, and then the structures become much more, let's say, complicated, and the properties, I'd say, become much more interesting to study.
Okay.
Yeah.
So another question from Gary Falia on YouTube. I thought uranium is radioactive. How can it be used for creating a superconductor?
That's an excellent question. Yes, uranium is radioactive, but it's actually not that radioactive. So it is safe enough to handle in our lab. And in fact, as far as radioactive materials are concerned, it's actually very safe to use. So this is not something that I would encourage you to do at home. but we're able to do this safely, and we're one of the few labs in the world that are able to do this. So that's why we study it.
Oh, wow, that sounds really cool. So, Vanshiba on YouTube asked, can you talk about some interesting biomaterials being developed to help tissue or organ transplants?
This is an excellent question, but I'm absolutely not a biologist. I think this is inorganic chemistry, right? So in biology, most of the scientists deal with molecules rather than compounds. It's also an arrangement of atoms, but the shapes and the properties are somewhat different. So perhaps this is a question for some of the other participants.
I mean, let's see if maybe some of the other speakers of today can actually answer it. Becky asked on Facebook, do we have to find and identify new elements to find superconductors at room temperature, or can we combine elements for this?
Yeah, so I think the safest way is to combine the elements, because you see this bottom row in the periodic table, these are all synthetic elements, so we can't really use them in the lab because they only live for a very short amount of time. So in principle, I would encourage people, and I think this is a common idea, to try and use the elements that we have in stable form and mix them together.
Okay.
That's the plan.
The next question comes from Ilenia on YouTube. What in your experience have been the hardest conditions you found yourself in whilst working with a particular compound in order to understand its behavior?
Yeah, this is an excellent question. So one of the elements that I also work with is mercury. So mercury, as you know, is highly toxic. It's also liquid at room temperature. So if you drop mercury, it tries to run away from you. So it is quite difficult because one has to be very careful to make sure that where you work is safe for both you and your colleagues. So everything that we do is in a very special contained box. And this is how we make sure that all of our elements stay at work and we don't bring them home. And a lot of these materials are also very air sensitive, which means as soon as you take them out of this box, they start to decompose. And this is also something that we're working on to try and make it easier.
I see. So you like to work with difficult materials in your lab.
In principle, yes. This is also somewhat of a theme of mine. Yes. Yeah.
Okay. The next question was asked on Facebook by Kumal. If we combine two elements from the periodic table that are the complete opposite, what will be the outcome? Will they delete themselves?
No, I don't think there's such thing as deleting themselves, right? So all the elements are composed of atoms, and within the atoms we do have positive and negative particles. But if you add the elements together, it's not like you're adding charged particles together, right? So they don't necessarily cancel. Now, there are some elements that are more or less likely to form compounds. That's a different question. But in principle, if you add two elements together, you typically make a material.
Okay. Salmon also asked on YouTube, do you work with special machines at your laboratory?
Yes, we have a lot of very, very cool machines, which I wish I could bring you to our lab and show you. They're able to reach very, very high temperatures, so temperatures that are comparable to the surface of the sun, for example, so about 4 to 5 degrees Celsius. And we're also able to reach very low temperatures, something close to absolute zero. And these machines are either for synthesis or for characterization. So we have a very large set of tools that we need to use in order to be able to understand our materials better.
Okay. So the last question for today, unfortunately. What is the current limit of superconductors? And is it possible to develop better ones?
Yes. So the current limit is about minus 70 degrees Celsius, right? So very, very, very cold room. Of course, I think there's nothing that's stopping us from trying to find new high temperature superconductors. And this is the dream, right? I can't tell you the exact recipe. If I could, I would have had it already. But in principle, the goal is just to try and keep on pushing.
Yeah. So thank you once again, Eteri, for this inspiring talk. And also thank you, our audience, for your questions